materials, having a look at our net list and our pin list, and then moving over to the PCB design. Also just do a couple of little things to get our schematic ready. So without further ado, let's jump right in. Now I need to save this. Let's just save again. So here at the bottom, you can see is our Arduino dev board. When last we save it, it was just now. And what else can we write? Well, we can write a bit of text and something. This is the design of a Mega 328P. Microcontroller. So let's just change the level because I don't want it on the wiring. I want it in the no. And I wanted click apply and have it here. Now, the next thing we can do to have a look, obviously, we keep on running the ERC check. See, we have a warning here. Power pin is connected to power pin connected. That is fine. We can approve that. Now, why does this probably come from? This connector that I made, this output I've created as a power pin. And this is connected now to this element here, just so it just where this is then connected. So this power, it just wants to make sure that I created this net called power, and it's connected to the power in here. Now, I know this is correct, but I just needed to approve that it was correct. Now we can export a couple of things. Let's export a netlist. Let's do documents. Create a new folder. Arduino dev. And we can save it here. Arduino dev. That was the netlist. Let's also export the part list to the same. Arduino dev parts. And let's also export the pin list. Just so we remind ourselves what all of this is. And let's just do an image as well. Why not? Arduino dev. We can save an image. We can have a look at what that looks like. And then we can also export the bill of materials, text, parts, save that also in our dedicated folder that we've created. Yep, wrong one. And save. So let's have a look at what that looks like. I'm just going to be opening up here on my own computer. You can't see it at the moment. So this is all the things we just exported. The first one here, let's open up with Notepad. is our net list. It's probably a bit here. And we can see all of our net list and all the pins that are connected. CL diode, ground, and all of these nets that we have created. So we know exactly where all of these nets are created, which pins are connected to which net. And this is very helpful information when we want to decide or we want to assemble our board. This is the picture that we exported. This is the picture of our device with all the connections made. This is our parts list. Let's also open it with Notepad, telling us what all the parts with their names, C1, 2, 3, 4, and 5, what their values are, what the device are, and what package they use. So we can use the parts list to order all of our equipment that we need, all the components we need. This is the pin list. Let's also open it with this now, all of my components just tells me where they are connected and to which net every specific pin is connected. So for my one IC, pin 1 is connected to this, and this is my my custom-made element. I can check P1 is connected to reset, P2, PD0, and so on and so forth. And lastly is my bill of materials. It looks a lot like the parts list. They are basically the same. They give you the same information, the part, value, device, package, and also a short description. And that is all of the exports that we can do. And all of these exports give us more information about our circuit. Usually when I design my circuit, I export everything and save it inside of a folder with that specific circuit's name on it. And then that just helps us to have a reference if something goes wrong to our board. We have a reference which you can use and use that to either fix our board, maintain our board, and assemble our board. So all of this is very important, very useful information. But we will now close this. So there's nothing more really that we need to do from this end. Everything is connected. All of our electric checks has passed through. Everything has got values and footprints. Next thing is switch to boards. We can either press that button or switch to board here. I usually like just clicking that. And it asks to create the schematic. And I tell it, yes, go ahead, create the schematic. And now we can see all of our components created and placed inside here. So we can see what we can do now is we can move everything down, or we can first decide what size board we want. Now, it is obviously a little bit hard to decide how big of a board you want. Usually you will have to see what your manufacturer, what their costs are, or how big you can get your board, how small it is, and just see what it costs. Usually they have standard sizes, the manufacturers, that would tell you how much boards cost. If you have no idea, then I would suggest just move in the elements in roughly the positions that you want. Then you can draw an outline before. So usually I start with, I like starting with my power connectors. So I would like to have this circuit done first. So I will have, that is my in connector. I would like to move it. And let's move it to somewhere here. Then I can see how big or small I have my board. And you can see if I move it closer, it tells me there is a bit of a problem. So I can have my connectors There. The next part that it goes to is through the diode. Goes through the diode. The diode then goes through the power regulator. And then also a couple of capacitors. We just check, see C1 and C3. Perfect. So we go and we pick out C1, C3. There is C1. Should be here. C1 and C3. So I'm not going to make the same mistake again where I have my writing that is that overlaps like we had in our previous board. Now I can move around the writing a little bit and make everything a lot nicer. Right, looking at the other side, we have C4 and C2. C4. Move C4. Thank you very much. Let's see if this works. And then C2. We move everything in a nice way like so. And then that goes to R1 and LED1. So we are looking for R1. There is R1. Move R1. Come on. R1, and you can see there you have the writing VCC. It tells you which net it's connected to. This is LED1. Now we move and find LED1. That's LED1 for us. And we can have it here. So this is our power delivery circuit. Next element we can move in our IC, place our IC down, and then have a look at our schematic. See, okay, so we need our little switch, our little reset switch, R2 and SW1. We have a look. There is R2. Oh, no. I want the whole component. So this is the reset switch. So let's have our reset switch somewhere here. Connected to our switch. Should be somewhere there. The next item of business, this only connected to ground of VCC. We'll deal with that in a second. Here we have our Q1, which is the clock. And also then we have our two capacitors, C5 and C6. So we have a look. Move in our clock. Now I like to have the clock as close to the microcontroller as possible. I just like doing that. actually have this configuration. So it does take a while to move everything in place, move everything around, but eventually everything will fit and will be fine. Right, the next item we need to move in is our connectors. So we have 1 connector, 2 connectors, and 3 connectors. Let's see where they can best fit. Click zoom to. Let's move this connector. And I see let's connect it to this side. See where this connector. So I see where these lines are connected. Have this connected here. The last but not least is the LED. This little LED. Have it connected somewhere here. And connected here. So now I can play a little bit around with the size of my board, move components. So I think the length is roughly correct. Let's move this to the one side. I can group a couple of components and just move them over a little bit. Group. I can move this LED here. Let's switch this around. And let's move this group. I have this group. I want to move it again. Right click and move group. Move this a little closer. So only thing that I'm doing is now just making sure that my board is nice and as compact as I can possibly make it. Let's have an element there. Okay, so let's change the shape of my board. I don't want that. Now to change the dimension of my board, I have to work on the dimensions layer. And now I can just create my custom dimension. I like to have right angles because I can always change it a little bit later. And have it like so. I can move around these connectors. Now I do have a little bit of wasted space here, but don't worry, I'll use it for something else. I can meter out the ends of my board. Click on meter. I want to have rounded edges around about 12.5. Okay, so this does not work. partly because it does not see this as a board. So let's start over before everything is said and done. Let's dimensions. Right. So let's try metering now. A little more of an aggressive angle. You can see I'm smoothing out all of the angles. I've decided that I'm going to be attaching my board to a certain area. So I want to drill in some holes. Let's have it. Let's change this to millimeters. 1. The hole that I want. I add in mounting holes. And this mounting hole will be just there. Next, I can have some writing. And this is our at Mega 328P dev board. I don't want it on dimensions. I wanted to have it on the top place. I can change the shape or the size. Let's press Shift Enter and press OK. Brilliant. Let's have it there and also add a version 1.0, so I know which version I'm working with. All right, now we can start connecting up all of our wires. Now this is usually easier said than done. As we spoke about last time, you have to now think about how you're going to be connecting your board. Now, most of my components are, well, all of my components are through hole. That means that it is easier to have all of my circuitry, all of my tracks running on the bottom side. Because as we spoke about, it is very hard to attach a through-hole component on the top side. It's especially for ICs and these connectors, I suspect, it is really, really hard because they're designed to sit flat or flush on the board. So it is very hard to get a soldering iron on the pins. So for this design, I would mostly work with the, well, mostly, I will almost exclusively work on the bottom side. And we'll see how far we get. If we can, we do all of the routing on the bottom side. So let's do all the routing on the bottom side. I'm going to start with my power connection first. Click on route AirWire. I can select its width. This is going to be a relatively thickish one because this is where all my power comes in. I walk around exactly what I want. And I need to route it on the bottom side. Let's just change that. Route on the bottom side. And I've connected those two elements there. Also, from the diode, I would also use a relatively thick connection. And then finally, this is also connected. And now this is nice and connected. Now I'm not going to be connecting the ground connection because I'm going to be using the full method to do that ground connection. So wherever there we have a ground connection, I don't worry about it all that much. Here we have VCC. So this is, I can see it is better to swap this or rotate this around. Let's move this. Well, we can actually leave it there and just move this down there. And now I can connect my AirWire again. Now this does not need to be 1 mil. I can have this as 0.5 mil. And have these connections. So how do I know the size for these wires? I don't really. What you actually have to do is do the calculations and see how much current runs through those wires. I don't really need that now. I know that what I'm doing is correct. I know that this thickness of a track, because it's a pretty thick track, will be more than enough to sustain the power. So usually when we are dealing with power, we would tend to make our tracks a little bit thicker than we would normally do. So thicker tracks means it can handle more current, and your power circuit will handle all the current, and then that current will then be divided up through your microcontroller and usually have small amounts of current. So in your power circuit, your power delivery circuit, you usually have thicker tracks to handle more current and more voltage. So this is also VCC. I can also connect this up to my VCC tract there. My going through this resistor to the LED. And then VCC should also be connected through here. So we have this connected to my VCC net. And also this is connected to VCC. I like having it run right through the middle. And that's also connected to VCC. Now, I think I have an idea now. The these signals that run through from my microcontroller usually do not need that much power, so I can reduce the size of my tract once again, and then I can start just creating these elements, connecting up these elements, reset. Now I can route multiple air wires. This one, this one, this one, and this one. And why not this one? That does not work so well. Doesn't matter. Let's just do them individually. So let's have a more of this effect. Our clock. Ground connection, clock, and clock. You see it automatically looks for select the best path here. And the best path there. That is ground, so I don't care that much about it. And connecting it there. Now the next is connecting the other pins. And it's easy as just selecting it and then selecting it. I can run it a little bit more manually, but I don't really need to. It creates relatively, that's a ground connection. That's a VCC connection, so I can then upgrade that to a little bit thicker. VCC. Then we're back to creating our normal signals. Right, what is left? It looks like just our ground connection. Oh, that's also a VCC. Ground, ground, and ground. We can obviously check our air wires. It all seems to be the ground. Okay, so let's create our full pattern to fill our PCB and make our ground connection. So once again, we choose the polygon. We choose our bottom layer and we draw our polygon around our whole circuit. And it is G in D. Click OK. And we click on Rat's Nest. And now we have connected all of our ground connectors. See, if we just find, this is a ground and it is connected. Click on manufacturing and it shows us our board. Look at the bottom side. And everything is connected and is pretty much perfect. Hopefully, let's click on the, ERC. There are no problems. So now our design is ready to be sent to the manufacturer. And now from this space, now a lot of people are a little bit afraid that if they have their components, that the board might not fit. So there is a little trick that you can try if you have your components already. The trick that you can try and do is to print out this board. Now I'm going to try it. I haven't done it with this yet. PDF. Okay, let's see if this works. So let's have this here. Let's go to print. Let's print everything here. Alignment center, print. Don't want to see. Let's the bottom layer for now. And then we will print, click on print. We have this print, we click OK. Now we call it something else, whatever we want, and we print it out. Now, the next thing that you should be doing is, let's have a look there. Just give my computer a little bit while to figure out. Now you have a PDF version of your board. What you can do is now to print that out on a piece of paper. And then you have a one-to-one scale model or representation of your circuit. What you can then do is then you can then stick your components through the paper, fitting in the holes that you see there. If I just share my screen. Putting in the holes that you can see there, because this is a one-to-one representation of your circuit. So these holes should represent 100% what your circuit in real life should be. So when I was studying and I didn't have lots of money to constantly redo my circuits, I would always print it out first and stick my components through the paper to make sure that it fits, that all the components that I have fits, because I didn't have enough money to just keep on buying new components or redo my circuit board. So it's a relatively easy way, well, not easy way, but a cheap way to make sure that all of your components fits into your board. So, right, just closing this down. So a lot of the times now we can either you can send them this BRD file, because if I save this, this is my Eagle BRD file, or I can also click on CAM processor, and this prints out the Gerber files. The top copper, bottom copper, profile, solar mask, all that kind of stuff, and also the drill file. It will print everything out or save it. Let's click on process job. Let's click on process job. I just want to see. It'll save this here. Click on advanced. I don't want to mirror anything. Do that. Let's process the job. It's fine. Let's go to our Arduino dev board. Select this folder and process job. So now we can open up that specific folder and have a look at our CAM outputs, our Gerber files, and these are all of our Gerber files. Now, the next step is we can check our online Gerber files. We Google it, we go to some website where you can have Gerber files. I click on this. Let's go to my Gerber files, Arduino Dev, CAM outputs, Gerber files, and let's select every single one of them. Opens up and I can have my Gerber files. So it looks, everything looks kind of fine. Let's also upload the drill file. Let's see if we can do that. And that's the drill file. So now I have the drill file. And everything looks fine. So what we've just basically created is that we've created our Arduino development board, our very own one that we can customize as much as we want, add in more components, take away more components, add in more memory, whatever we want. But as you can see, it wasn't that difficult to do. And I'm reasonably sure that this will be a really good project. You can also add in other things like a programmer, because that's one thing that this one does not really have. But you can add in a USB port, all that kind of stuff to make your project better. Now, for the PCB manufacturers, that you can send them. Obviously, you can send them sometimes you can send them your eagle.brd file, and that would be in the project folder. You have the SCH, with the schematic file, and the .brd file. And yeah, you can also save that as an Eagle file. And like I said, the Eagle files are the most common files that you can use for creating PCB. So most manufacturers will accept Eagle files. And also remember the drill files, because the Eagle file shows you how the copper is on the couple of layers, also with the solder mask and the silk screen. But the what do you call it? The Eagle file does not contain the drill file. You have to also send over the drill file. But usually the manufacturer will tell you, oh, please send a drill file. But in any case, let's take a quick 5-minute break, and then we'll come back and then we'll wrap up the whole course and talk about the exam. Right, see you in 5 minutes. Come back. Right. So we've just completed the design, and as you probably have seen, I did most of the work, or all of the work, on the back side. And that, just to remind you, the problem I had with this circuit is that I did for the through-hole components, I did some tracks on the top side and some on the bottom side, and those tracks are not connected. So if I have got a IC connected, for instance, on the top and the bottom side, that means I have to solder it on both sides, which is very difficult, if not almost impossible. And I just, now this design that I just created, I mean, it was easy enough to route everything on the bottom side to make sure that everything is connected and does remain connected and are easily joined. But it does also happen that if I do not have that much time to spend connecting everything up and thinking about it, I just use the auto connector or the auto connecting tool. The auto router, it is called. And a lot of the times, the auto router will use the top and the bottom side to connect, because once again, it just uses mathematical equations to find the shortest paths to connect to the points. So it doesn't really care, and it doesn't really understand that you probably would like to have not have your that you cannot really assemble something that's solid on the top side and the bottom side that much easily, or that easily. Right, so we'll do a very lightning quick recap of everything that we just did, or everything that we spoke about. And then we'll quickly talk about the exam and what I expect. Now, I do realize that you are going on holiday, I think, as of tomorrow. Can somebody just write in the chat the dates for your holiday? Because I don't like giving an exam project during the holiday. So while I'm talking about the things, can somebody just write in the chat what are the dates for your holiday, so I can give you the exam after the holiday. Right. So I'm sharing my screen once again. You should now be seeing the presentation that I did all those weeks ago, and we'll just go through it quickly. So once again, the overview, it is just simulate circuits, design circuits, and create the PCB. We talked about what a PCB is. We talked about the materials of PCBs and what they are made of. And you have to remember that everything electrical, so though that we're connecting our tracts, they still have resistance. So we try and make our as we possibly can, because one wider tracks or a bigger conductor means that the resistivity of that conductor is lower, and if it's shorter, it's also lower, as you can see by this equation. The surface area, so if we make our tracks bigger, we have a bigger surface area. And L. And we spoke about different materials and also about silver tarnishing and copper tarnishing. Now, that's another thing you have to remember when you are creating your circuits. Now, a lot of these companies help you out with this. But if you have a copper circuit or a silver circuit, if you go that route, then you have to bear in mind that those circuits do tarnish over time, meaning that they chemically react with the atmosphere and then they change their resistive properties or their electrical properties, let's call it rather that. And if you design a circuit, you want to have it the same functionality throughout its lifetime, because if it changes too much, the operation of your circuit might change. Let's say you have a couple of comparators comparing voltages or something and then creating an output. If your electrical characteristics change, then those voltages or over the comparators do change, and you might get some unexpected behaviors. But most circuits we have is usually a combination of copper or brass, and then the pads or the electrical connections exposed to the atmosphere are usually coated with something that is not that not that responsive. Once again, the tracks are the connections or the physical connectors between the our components. And we also spoke about this table about how thick a trace is and how much current it can take. Now, once again, a lot of these tables that you might find are just like estimates. So take it with a pinch of salt if you have, if you look at these tables, but usually they should be fine. But if you have a line or a trace that carries a lot of current, just make sure to just increase it a little bit more, because a couple of things might happen. If the trace is too small for a certain amount of power or current running through it, it will heat up, generate heat. That means a power loss. And also it might physically melt the copper tract. So the tract with that's attached on the substrate or the backboard, it might melt, or it might lift up from the substrate, and then once it cools down, it'll crack, and you will have a very bad circuit. So bear in mind, make sure that you understand what is happening in your circuit, just so that you can have ensure that your circuit will work under all circumstances and will not create excessive amounts of heat and have that as a power loss source. Then we spoke about circuit diagrams. And this is just the schematic representation or the symbolic representation of an electrical circuit. And this is the first step that we have when we are the schematic, and there's something we've done quite a few number of times already now. We spoke about basic electrical rules, series circuits, parallel circuits, total resistance. And we also spoke about simulating these circuits. Now, I will be asking you to simulate an analog circuit and also a digital circuit in Eagle. The circuits that I'm going to give you are relatively simple, relatively easy, but just as a quick overview of how to simulate circuits, in case you've forgotten, I'm sharing my screen once again. As you create a new schematic. I'm not going to add in anything else. You go to the libraries, and all of the libraries that deal with simulation starts with the ngSpice. So you scroll down and you look for ngSpice, mgSpice, simulation elements. So I can have my resistor, have a couple of resistors connected in any way that I want. I can have a voltage source. And I can connect all of my circuits up in a fashion that I would like. So I can connect everything up. Importantly, for any simulation circuits, I need to have a ground connector. Voltage switch, VSS, ground. There we go. And change that to ground. I give all of my circuits values. 200, it doesn't really matter at this stage. This is just a demonstration, a quick demonstration at that. 250. And then 500. Why not? I have my source, let's say 12 volts. Up here, I can have voltage probes. Let's have a voltage probe there, voltage probe there, and a voltage probe there. Why not? And let's have one there as well. And remember now, this is the net name, so I can rename my nets as we already do. And this is net, just as an example. I can set up my analog source. It already has a DC value of 12, so that's really all I want. And I can click on simulate. Usually with this, I can have either at the operating point, meaning that it'll calculate all the values at 12 volts. I can click on simulate. And here I will have all of my voltage values. 12 volts, 9 volts, 8 volts, and so. And if I actually close this, here we have, well, we don't have the voltage values, but we simulate again. We have all of our voltage values here. This is our variable, so this is N1, and so on and so forth. And this is now how we simulate. Also go to ngSpice, but in this case digital. You click up the gate. This, you need a digital source, DIG-SRC. This is digital source. That's exactly what I want. You'll have to set up your digital source. Times 0, 1, 2, and 3, for instance. 0, 1, 0, 1. Save setup. Digital source 0, 1, 2, 3, 0, 0, 1, 1. So I have my time, and at that time, it is giving out a certain signal. I just give a little output tail. I connect my digital sources to my digital gate. I have a voltage probe there, and then I simulate my circuit. Now here I will have to use transient, and it's got 4 seconds worth. Click on simulate, and it gives me my output. Now, if I want to have seeing what my input is, I just add in a couple of voltage probes. And I click simulate again, update netlist, simulate. And this is my input signals and my corresponding output signals given here. So remember, this is how I simulate my digital and analog circuits. And you will be getting a question about simulating a digital circuit and also an analog circuit. And then I'll ask you to give me the voltage values. Well, give me the circuit that you've created and also voltage values or logic values at certain elements or at certain times. I don't want to save that. Right, back to the presentation. And then we spoke about prototyping boards. I mean, about creating a circuit on a breadboard first. And you can create quite complex circuits. And then if you want, create a circuit on a strip board. And then after you've soldered everything to your strip board, testing it, and then once we're happy, then creating your PCB circuit. We spoke a little bit about soldering and also pick and place machines, like here on the right side. Now, pick and place machines are very, very useful. And remember, when we have our Gerber files, you can also export a solder paste mask. Is it a solder paste mask? And that is information for the manufacturer where he can place solder paste for your SMD components. You can also ask a manufacturer to assemble your board for you. You provide them with a bill of materials or a parts list. They will source the components, attach the components to your board, test it, and then send it back to you. And you have a already assembled board for you. But it is more expensive than doing it yourself. And soldering is like the physical act of creating the electrical connection between your circuit and the board. And these boards can come in all different directions, and you can have a custom board shape. And we also spoke about PCB manufacturing methods. I spoke about the etching method where you can create your own boards by hand. But then again, I reminded you, please be very careful because it can, well, it does involve using acid, and it is very dangerous using acid because it can burn you. And then the easiest way is having somebody create your board for you, like I did for this project here. I sent my design away, my .brd file away. They sent me a confirmation, and then they created my board. And this is a very, very high quality board, and it wasn't that expensive. But also, the more boards you order, the cheaper the price per board is. Usually going for a prototype board like I did now is not that cheap, but in comparison to buying the acid kit and all those other things to create your own boards, it is actually not that expensive. Then we spoke about multi-layered boards. Now, with the version of Eagle that we are using, we are only limited to 2 layers, but you can have a very large amount of layers. But usually we stick to 2 layers for this level because, I mean, you can do a lot of connections with your 2 layers. We spoke about the solder mask, the green resin covering that protects your circuit. And then we spoke about the silk screen. And this is the silk screen. This is the information that we have on the board, also showing us where which components go. And as you can see, components R1 generally refers to resistor 1, C1, SW1, usually a switch, This is their revision 3.1 of a PIC user interface. And it also uses a 2 gig max SD card. So on this silk screen, you also add in a lot of information. On this board as well, you can see it's got mounting holes here on the side. The bigger holes usually are for, this is usually a USB connector. So usually if you have connectors that go in and out of elements, you would usually have these bigger holes also that provides more stability for your board, because you'll be connecting a USB, for instance, and then yanking it out, and the whole connector shouldn't break your board, hopefully. We then spoke about components, the different types of components, and also different types of packages. So this is usually the dual inline package. We got, this is the T220 package, TO220 package, and also different packages for transistors, diodes, and every single component has got a package type. Now, Eagle does have most of the packages like we spoke about, but a lot of them they don't have. And then we went about creating our own packages and our own components. Now, these aren't that important. Important to say that resistor and a surface mount resistor perform exactly the same operation. They aren't really different from each other. They are the same component. They perform the same function. They have the same resistance. They're just, the only difference is in the way that they attach to the board. And we also saw an example of how a through-hole component can be bent to be used as a surface mount component. I like through-hole components a little bit more because in my mind, they are easier to solder and attach to the board. Whereas with surface mount components, you can make your design a lot smaller, but the components are harder to attach. But on the other side as well, it's very hard for a machine to insert a through-hole component. It is easier to insert a SMD component because it is a flat component that it can just lie flat like so. We spoke about the resistance, voltage, current relationships and how important it is. And we also spoke about resistors, through-hole, SMD, and also the resistor network, which I also used in my design. Please be sure that you know how to identify the resistance of a resistor by using the band code. And also, if you have a surface mount resistor, the numbers on those resistors also indicate their specific resistor. It depends on how many digits there are. That will then indicate the specific specific resistance of that component. And please be aware that you also have 0 ohm resistors. And we spoke about that 0 ohm resistors are used as sort of like connection bridges in your PCB. So let's say I've got a PCB that is very hard to connect. I can use a component like a resistor, like a through-hole component, to create a bridge from one side to the other side to make my connections a little bit easier. Now, excuse me, I'm just thinking. Now, Yes, that it would essentially involve you also using the you can also use a jumper wire, like a connecting wire, but wires aren't that nice if you have it on a board. It doesn't look so professional. And also wires have a tendency to break a lot easier because if you move around the board a little bit, those wires can get caught in something else and then snap off. So we usually have 0-volt resistors, but they are basically just connecting wires. We also have inductive components, capacitive components, and these can all come in through hole and surface mount components. Also spoke about that capacitors, especially, please be aware, some capacitors are polarized, meaning that they not polarized they do have positive and negative poles. And if you, especially these electrolytic capacitors, if you connect them in the wrong orientation, they will, well, they won't blow up, but they will be damaged and cease to operate. We spoke about these integrated circuits. We created one just now, and this is the surface mount chip of the one that we just used, I think. Yes. And here we have different package types. The DIP, dual inline package, SIL, MPF, single inline multipurpose dot function. I think SDIP, dual inline picker. All of these designations means a slight difference in the mechanical dimensions of these elements. And like I said, sometimes it's really hard to find the correct package type. So that is why most often I just do it myself. For the component that I decide I want to work with or use, I get that component and I draw a very specific or a custom schematic and also a custom footprint that I know fits for that specific component. Because Eagle is great. Most of the components in Eagle, if you can find it, does work. But with these IC packages, there are so many different packages around that you have to ensure that you are using the correct packages. And we also spoke that there are hundreds and hundreds and hundreds of types of connectors. And we spoke about that there are different types of softwares you can use. We are using Eagle. That'll change to the newer updated versions. You can use KiCad, Multisim, Proteus, and all of them are slightly different. But as I keep on speaking about, I was taught KiCad when I was studying, but it is relatively easy to move from one program type to the other program because they all basically do the same thing. And they all start with the schematic view, and then from the schematic, you create your PCB file. And if all the components are connected correctly, then the PCB is also relatively easy. You move your components inside of a selected area or a board outline, and then you just connect it, save it to a Gerber file, and then it's basically all the same. So the point is, if you can do EagleCAD, you can do KiCad and OrCAD and all those other things. The being retrained in another program is relatively easy because, like I said, they all do roughly the same thing. And then we spoke about different types of PCBs. It's really not that important to go through. And Here you can probably now recognize you have mounting holes. This is a connector. This is a huge capacitor with some diodes at the bottom for some other reason. I don't know why. And you have a bank of resistors, some LEDs, an IC, and the blue, I would imagine, is the bottom connection, and the red is the top connection. And here you can see the top connection is not connected to any components. They are simply a bridge between one element, one tract, and another tract. So in this person's view, on this person's case, it is just using it as a bridge between tracks. So now you can see, if you can see this, you're like, okay, I kind of have an idea what is going on. Same PCBs can be round and really intricate and really small. You can also have your components at different edges. It does not need to be at 90-degree angles. You can specify the angle of your components. And PCBs can also be flexible, but be aware, PCBs might be flexible, but the components or the ICs probably aren't. And we spoke about all of this. Brilliant. So we ran through that whole presentation in what, like 15 minutes? Right. Now I'm going to be speaking about the exam project. So I'm going to find out when your vacation is over. When your vacation is over, I will send you an exam document coupled with some instructions. Then you'll have about, I think, a week's time to complete the exam in the way that I specify, and then you'll send it back to me. I'll mark it. All do very well. I am 100% sure of it. The exam, I'm not quite setting it up quite yet, but it usually is like four or five sections. The first section usually is a relatively simple circuit where you create a schematic that does something. And then from that schematic, I will ask you to create a PCB file, create like a bill of materials and a couple of questions around that specific circuit. Then I'll probably ask you, I think, I'm not sure yet, to do an analog circuit simulation and also a digital circuit simulation and some questions around that. And also, lastly, there will be a more complex PCB design where I will once again ask you to do a schematic, and also after the schematic, create a PCB file. So I will set all of that up, and I will send it to you after your vacation is done, because I like students to have some time off that they don't really, that they can just have some time off and just enjoy their life. What I will do now is I'll send an email to everybody reiterating what I've just told you about the exam. I'll also give you some things you can try and do to just exercise PCB design and PCB layout, some circuits that you can try and do. And then that is it. If you have any questions at all, please ask, send me emails. But like I said, I will send an email detailing a couple of the things that I've just told you. But importantly, the exam will be a project that you will have a set amount of time to complete. It's usually like 5 or 6 days, so you can do that in a relaxed manner. Why is it in a relaxed manner? Well, I've never, ever in all of my working life have a boss rushing in, give me a piece of paper and tell me to complete that within 2 hours and then run off without telling me anything else. So whenever I'm doing a PCB design, I have enough time to design the PCB in a relaxed manner and check myself, check my errors, and design it in such a way that I have enough time to do it properly. Usually with a PCB design, it'll take a couple of days, it'll take a couple of weeks. You'll design and redesign, design and redesign, and the process will take really long. So I don't really see any use of giving you a test that you ask you to do something in 2 to 3 hours. It doesn't make sense in this specific case. So for the exam, you will have a set amount of time, but it will be a couple of days so that you can create the circuits and the PCBs that I ask, and you can do that in a relatively relaxed manner and send the results that you have back to me. But all that information will be contained in the document that I send you guys. But for now, I hope that you've learned something about PCB design. It is relatively simple, but as with anything, the better you get, the more complex circuits you can design, and the easier it is when you are designing circuits. That is it. If you have any questions, send me an email or anything else. I will, like I said, send an email detailing everything I've told you. And that is it from my side. Have a wonderful holiday. If this is the last class you have before your holiday, I hope you have a wonderful time, relax, and after the holiday, I will send down this exam. Right. Thank you for listening, everybody, and I look forward to receiving your exams when I send it over to you. All right. Bye, everybody.